Hi, this is Professor Fernandez. In this video, we are going to work on 3 examples of using integration by parts. These examples come from the lesson notes from lesson 21 in this Calc 2 course. You'll find those on this website and also these other resources. So integration by parts is, well, let me first of all say that we are now, if you're following this playlist, in the integration section of this Calc 2 course. In the lesson before this, we talked about use substitution. So that is the first method, maybe the last method you learn in a Calc 1 course. We kind of go through it again in a Calc 2 course. And it is an integration method. So the idea is if you meet an indefinite or definite integral, right, it is the first thing that you might try after possibly just using an integration formula like antiderivative e to the x is e to the x. Integration by parts works similarly to use substitution, but it's a little different. So I'm going to zoom in here on the right-hand side, review that just real quick. This is kind of the standard way you'll see integration by parts presented. So you'll notice that on the left-hand side, right, we have the assumption that whatever integral you're working with, let's say it's x e to the x. The first example we'll do in a minute. Whatever integral you're working with, the assumption is that you have chosen a u, and the rest of what's in the integrand is therefore dv. So for example, for this one, we have to make a choice, kind of like use substitution, of what u is. And for this particular integrand, there are only 2 options. Either, well, I mean, there are 3. Either u is x, u is e to the x, or u is the entire thing, the entire integrand. So, you know, I guess there's another choice of like u is 1, which is also in the integrand, but we don't see it. So again, the question arises, you know, how do you choose u, right? Some of these u's will lead to a successful application of integration by parts. By that I mean you work out this right-hand side over here, and it's simpler to work with than the integral you started with. That's what I would call a successful application of integration by parts. Some of these u's will do it, right? But some of them won't. And how do you know which one will actually help you out? So I'll address that in a minute, but let's just look at what happens with integration by parts itself. So after you've chosen u and the rest of the integrand is du, there are, so I'll write this down, these steps. So choose u and dv. After you've done that, you have a couple of things to do. You have to calculate u prime, the derivative, and you have to calculate v. So going from u to u prime, that's differentiation, so you have to remember your derivative rules from Calc 1. Going from dv to v, that's integration. So you have to remember some of your integration facts from Calc 1. Once you've gotten all this information, u, dv, and u prime and v, then this is literally the integration by parts formula, right? So your original integrand equals the product of u and v minus the new integral where v is being integrated with du. Okay, so we'll see all of that in a minute in the example. Excuse me, and the last thing that I would mention about integration by parts to give you some intuition as to what's going on. dv here is the differential of v. Think of it kind of like the derivative of v. It kind of is. Notice that on the integral that's on the right-hand side, the differential derivative is on u. So one way to think about what integration by parts does is that it changes the derivative from v to u. Right? It was here on v, and over here it is on u, and it does that exchange of the derivatives at a cost. First of all, there's a minus sign. This integral didn't have a minus sign in front. This one does. And then there's what's called a boundary term. So this is, in effect, left over from that process of exchanging the derivatives. That is not, this way of viewing integration by parts is not something that's necessarily going to be so helpful in this course, but it shows up a lot in the sciences, especially in physics and chemistry when you treat integrals using integration by parts. Okay, so let's head on to the examples here, and let me return to this question of how do you choose u? So there's a big red box here because I wanted to address that layer by layer, right? So choosing u. There are many, many ways that you could think of to choose u, but there's a nice rule of thumb which fits into the acronym ILATE. So fitting for a student, right? You don't necessarily want to be late for class. If you have a good reason, sure, that's fine. But generally, you want to be on time. But if you're thinking, you know, I am going to be late, right? This actually turns out to be a pretty good acronym for integration by parts. And what does this mean? This acronym reminds you that when you do integration by parts, a good rule of thumb is to choose u to be the first function in the integrand in this list from left to right. So if there are any inverse trigonometric functions in the integrand, try u to be those first. If there are any logarithmic functions, that's your next choice. And then if there are any algebraic functions, that's your next one. Any trigonometric functions, any exponential functions. Okay, so it's choosing u is choosing the first function in the integrand that appears first on this list from left to right. So I'm going to leave this there so that we can use it in the examples over here. So now let's go back to that initial example. So antiderivative of x e to the x. Okay, so if I'm going over here to the acronym, I have to identify the functions in the integrand. X is an algebraic function, and e to the x is an exponential function. So I have an a and an e, and I look over here, and my ILATE acronym, going from left to right, a comes before e. So my choice for u is going to be the a function here, which is x. So I'm going to choose u equals x. One thing I'll note right away is that this acronym, ILATE, and this way of choosing u is a rule of thumb, meaning that there will be cases where it doesn't work, right, where it leads you astray. But in my experience, this is rare, right? So it's a really good rule of thumb. So I would encourage you to start here in terms of where you would want to choose u. And then just to give you some intuition about why this rule of thumb, the exponential here is last, right? You want to choose u to be an exponential last, like a to the x, because the derivative is the same function, pops out an ln of a, dx. So this doesn't really help. It's kind of like u and its derivative are basically the same function. So in terms of integration by parts, one thing you want to do is you want to choose u such that when you differentiate it, it makes the derivative, it makes the integral you get for integration by parts simpler. Because remember, the result of integration by parts is that you have this du here. So you want to choose u such that its derivative makes the new integral a little simpler. And so if you have a function like an exponential whose derivative just doesn't do anything, it just regurgitates the original function, maybe with an additional number, that's kind of your last choice of u. That's probably, it's probably going to be the least useful choice of u, hence why it's last in this acronym. So that's just a quick little note about why the functions are ordered the way they are ordered in this rule of thumb. Okay, so returning to the example, we have u equals x, and so now everything that is left over in the integral, including the dx, is the dv. So that's e to the x dx. And then now from u, we calculate du. Remember, this is just the derivative of the u function. The derivative of x is 1, multiplied by dx. So du is f prime of x dx, where f is, whatever function, here, for example. Okay, so we have our du. And then dv, to get v, we integrate the function e to the x dx. We know that the answer is e to the x. Normally there's a plus c, but this is the one time the calculus instructor is going to tell you, forget about the plus c in the indefinite integral. Okay, because u substitution is really just finding another indefinite integral. So there'll be plus c's floating around. You won't need them at this stage for v. Okay, so at this point we have u, we have du, we have dv, and we have v. So now we apply our integration by parts formula. This says the original integral equals uv minus integral of v du. So I put in my u, so that's x. I put in my v, so that's e to the x, minus integral of another v, e to the x, times du, which is just dx. And this is the stage where you kind of have to listen to the math at this point, right? Math communicates to us. It tells us stories. We just have to learn to listen, and that's a skill that takes practice and communication and collaboration and work with others. So this particular math is telling us that we've done a good job, because the original integral we did not know how to do, we've now reduced to something that is just a term minus an integral that we know how to do now. We know what the integral of e to the x is. That is just e to the x. And now we get to put our plus c, right? So this is the final answer that we get for the integral of x, e to the x. And that's our first application of integration by parts. So let's do this again for the other two examples, and we'll see that as the functions in the integrand change, right, the choice for u may also change. So let's look now. Let me actually move this over a little bit, give ourselves some more space. Let's look now at the second example. So this is x ln of x. Okay, same idea here. So this is an algebraic function. This is a logarithmic function. And logs, again, going left to right, come first in this list, and then come algebraic. So this time, we actually want to choose u to be ln of x. Right? So let's choose u to be ln of x. We'll find its differential, du, is just the derivative of ln of x, 1 over x, dx. And then everything left over in the integrand, which is x dx, that is dv. So dv is x dx. V is the integral of x dx, which is just x squared over 2. Again, just leave out the plus c for now. Okay, so my integration by parts says this integral is equal to uv minus integral of v du. We have the u here, so ln of x times the v, that goes over here, times x squared over 2, minus the integral of that same v, x squared over 2, du, which is 1 over x dx. Great. So we have x squared ln of x all over 2 minus, I'll bring out this 2 over here, 1/2 integral of, and then we can cancel one of these x's with one of these, x dx. So x squared ln of x over 2 minus 1/2, and then we integrate this. We do our check. Our check now, is the integral we got simpler than the one we started off with? Definitely. We know how to do this one. This is an integral version of the power rule, x squared plus x squared over 2, and then we have our plus c. Okay, so simplifying here, we get x squared ln of x over 2 minus x to the 4th over 4. Okay, so that is our integral with the plus c. So that's the result for this one. Great. So again, you can see here in this example that x was the same function in both integrands. All I did was I changed the other function in the integrand. And because of the order of appearance here in our rule of thumb, I late, that changed what the u is that we would have picked. You know, a rule of thumb is a rule of thumb. Like I said earlier, it means that there are some instances where it may not work. It also implies for this content, for integration by parts, that there may be other choices of u that work. So for example, in the example we just did, if you chose u to be x, not ln of x like we did, and dv equals ln of x, you could still feasibly do this problem. You would just, ln of x dx, you would just need to know how to integrate ln of x dx. And this actually ends up being an integration by parts problem in and of itself. So it illustrates another point that you know we've seen before with u substitution, another integration method, right? Sometimes you have to apply the method over and over again. If you go to the example 21.2, you pull up the lesson notes for this, again, at that website above, over here. You'll see in example 21.2, you'll see me doing exactly that, applying integration by parts twice. To an integral, I think it's e to the x times cosine x. Okay, so to finish this one up, let's look at part C here. This is integral of x cosine x dx. We'll go through the same check over here for I late in order from left to right. So we have an algebraic function, that's x, and then we have a trigonometric function, that's cosine x. Algebraic comes before trigonometric here left to right, so we'll choose u to be the algebraic one, and then dv to be everything left over, the trig one. Okay, so we have du is the derivative of x, that's 1 dx, and then we have v is the antiderivative, the integral of cosine x, that's sine x, ignoring the plus c. So then we get u times v minus integral of v du, and then we just put in everything we know. So u is x, v is sine x, minus integral of the same v, sine x, and then du, that's dx. And then check, right? Is the integral we got simpler than the integral that we started off with? Answer is yes. So great, this helped us out. And then we're doing the integral of, and we can write this as plus integral minus sine x. In other words, we can put the negative sign, sign in there. Why would we do that? It doesn't really matter, but it's a little more helpful in the sense that this integral is not going to give us cosine. Remember, the derivative of cosine is negative sine sin x. Okay, so this is plus cosine x. Integral of negative sin x, right, is cosine x. And then plus c. Okay, and this is therefore our answer for the antiderivative of x cosine x. Last thing I'll mention, at this point, we've done 3 examples of integration by parts, and we've sort of illustrated this I-late. In the next video, you can see it kind of queued up down here, right? I will introduce you to a tabular method of doing integration by parts for when you end up having to do it more than once. But the last thing I'll mention for this video is that, fundamentally we're doing integration, indefinite integration. So you can always check your work, right? All the 3 functions that we got from this, if we differentiate them, they should each give back the integrand that we started with. If they don't, then that's a clue to you that one of 2 things happened. Either you made an error in calculating the derivative, which could happen, or you made an error in applying integration by parts or any one of its steps, which could also happen. But the point still stands. You can check your work, right, using just the fact that the derivative of the result you got should give you back the integrand. Thanks for watching.